Hello everyone, my name is Scott Blackburn and I manage automotive field applications engineering and business development for Vishay in the Americas. Today I'm going to talk about a unique reference design that's been developed by Vishay that can be used in any dual board net system. To get started, I wanted to take a minute or two and talk about the 48-volt dual board net. It's still an emerging technology, but it's growing quickly and will continue to do so. There are already vehicles on the road with 48-volt systems. They've been around in Europe for a few years now, and they're making their way to the United States as we speak. So when we talk about a dual board net architecture, we're talking about vehicles with both a 12-volt bus and a 48-volt bus. The 12-volt bus will continue to support the lower power loads in the vehicle, such as interior and exterior lighting, powertrain control modules, the infotainment system, and any other basic control modules or functions. There's already plenty of infrastructure in place for these types of systems, so we'll leave those on the 12-volt bus. The 48-volt bus was created for the new higher power loads in order to reduce the currents and keep the cost of wiring and other related components reasonable. These loads would include electric power steering, air conditioning, engine cooling, electric turbos, and any add-on parallel hybrid inverters for start-stop or traction assist. As I said, dual board net systems are becoming more popular, and we're going to need new modules and components to support these new designs. For example, you will need a high-power bidirectional 48-volt to 12-volt DC to DC converter to transfer energy in either direction between the 12-volt battery and the 48-volt battery, depending on the electrical demands of the vehicle and the state of health of the batteries. Therefore, Vishay has developed a 3 kilowatt, 48-volt to 12-volt DC to DC converter that can be used in any dual board net system. The design utilizes a buck boost topology to allow for bidirectional operation so that energy can be transferred back and forth between the 48-volt battery and the 12-volt battery as necessary. In general, these types of DC to DC converter topologies are not able to operate at maximum efficiency over a wide power range. However, this design features 6 identical modular power stages that are each capable of providing 500 watts. As you will see later in the presentation, it's possible to activate or deactivate the power stages separately to allow for the efficiency to be maximized under any operating condition. In addition, this design is also easily scalable for other applications by either adding or removing power stages to achieve the desired maximum output power. As you can see from the images on this slide, the design utilizes an insulated metal substrate for the power stage that is mounted on a heatsink for thermal management, and a standard FR4 printed circuit board for the controller that is mounted on top of the power stage. The design of both the power stage and the control PCB will be detailed in the remainder of this presentation. To give you an idea of the basic buck boost architecture, this schematic shows a simplified version of one of the phases of the power stage. The 48-volt battery connection is on the left side, and the 12-volt battery connection is on the right side. I'll go through this design in much more detail during the rest of the presentation. To give you an idea of the power stage layout, you can see the component footprints for each of the 6 identical phases, and the main connections for the 48-volt, 12-volt, and power ground located in the center section. Here's a little closer view of just one of the identical phases of the power stage, which I'll be using to point out more details as we go through the rest of the presentation. To give you an idea of the control PCB layout, you can see the component footprints for each of the 6 identical phases. Note that 2 common switching power supplies, highlighted in the red box, were used to supply 11 volts and 5 volts to each of the phases to power the required control circuitry. Here's a little closer view of just one of the phases of the control PCB with one of the switching power supplies, which I'll be using to point out more details as we go through the rest of the presentation. As I mentioned before, this is a modular design that allows the individual phases to be disabled depending on the load conditions in the vehicle to maximize the efficiency. The phases have been designed to operate at maximum efficiency at a 500 watt output. For example, if the vehicle load condition is requiring only 1500 watts, 3 of the phases can be disabled and the remaining 3 phases can be operated at full load for maximum efficiency. By comparison, if each of the 6 phases were operated at half power to achieve the same 1500 watt output power, the overall system efficiency would be much lower. Therefore, for any other vehicle load condition, the goal is to maximize the output power of each individual phase by using the minimum number of phases possible. In order to activate or deactivate each of the phases, 2 sets of high current MOSFETs are used. They are connected in a bidirectional arrangement so that when activated, current can flow in either direction depending on which battery is supplying the energy, and also to prevent the backflow of current through the MOSFET body diode when the switches are deactivated. Also note that these 2 sets of switches are used for a protection feature as well. In the event of a failure in an individual phase, it can be completely disabled and the system can be put into a limp home mode to avoid a total breakdown of the vehicle until the module can be replaced. On the 48 volt side, Vishay SQJQ184E 80 volt MOSFETs labeled TR1 and TR2 in the schematic were used. And on the 12 volt side, Vishay SQJQ140E 40 volt MOSFETs labeled TR5 and TR6 in the schematic were used, both of which I'll talk more about in a few minutes. Each part was selected for the lowest possible RDS on to minimize the conduction losses, since they are being used strictly for enabling or disabling each phase and not for high frequency switching. Taking a look at the layout, you can see the 2 sets of switches. Each pair is located as close as possible to the respective 48 volt and 12 volt battery inputs. As I mentioned a minute ago, both the SQJQ184E and SQJQ140E were used in this design. They are both trench technology MOSFETs and feature our PowerPack 8x8L package. This 8x8mm package utilizes a bond wireless clip construction, which provides benefits in several areas. It results in an extremely low junction to case thermal resistance of 0.25 degrees C per watt, which allows for a much improved thermal transfer compared to a wire bond construction. The bond wireless construction also allows for very high pulse drain currents, which is critical when you have overload or short circuit conditions at the load. One more point to mention is that the gull wing lead frame provides improved board level reliability, which is the ability to maintain their solder joint integrity over the life of the product as it's subjected to thousands of thermal cycle events. Even though it wasn't used in this design, I also wanted to mention that we have a top-sided or reverse cooling package that's available for applications where the heat needs to be removed from the top side through a separate heatsink rather than down through the printed circuit board to the heatsink using thermal vias in a traditional configuration. In order to implement the buck boost topology, a half-bridge connection was used for each phase, again using Vishay power MOSFETs. An important detail to notice in this design is that the high side MOSFET, labeled TR3 in the schematic, in a buck boost topology usually only operates at a fourth of the output current, so the on resistance is not very critical. More important is the gate to source charge, QGS, and the gate to drain charge, QGD parameters, which need to be minimized in order to reduce the switching losses which will dominate when operating in a switching frequency of 100 kHz to 150 kHz. As a result of all these considerations, a smaller package can be used for the high side switch as compared to the low side switch. In this case, a Vishay SQJ182EP 80-volt MOSFET in a PowerPack SO8L package was used, which I'll talk about more in a few minutes. For the low side switch, the on resistance dominates the power losses, so two of the SQJQ184E MOSFETs that were also used for the enable switches were connected in parallel to minimize the conduction losses. Taking a look at the layout, you can see the smaller high side MOSFET and the two larger MOSFETs connected in parallel for the low side switch. They're all situated as close together as possible to minimize any stray inductance or capacitance, and also to make sure the current is shared equally between the two MOSFETs connected in parallel for the low side switch, by having them stay at approximately the same junction temperature. As I mentioned a minute ago, the SQJ182EP was used for the high side phase switch in this design. This is a trench technology MOSFET and is in our PowerPack SO8L package. This popular 5x6mm package features a bond wireless clip construction, which provides similar benefits to the 8x8mm package described previously. An extremely low junction to case thermal resistance of 0.38 degrees C per watt due to the clip construction, very high pulse drain current capability to handle overload or short circuit conditions, and the same type of gull wing lead frame construction which provides improved board level reliability. Even though it wasn't used in this design, I also wanted to mention that we have a new dual bond wireless package in development as well, in the same size, for applications where two separate switches are required in close proximity and the thermal requirements can be satisfied using a common package. A little more detail on driving the power MOSFETs used for the phase switches that I just discussed. Sometimes small details like choosing a gate resistor get overlooked, but in this design it's fairly important due to the peak currents that are required to turn on these MOSFETs at very high frequencies. Using a typical thick film resistor might be a first thought when picking the gate resistor, since the average power is very low. However, it's the pulse capability that's the key consideration in this type of application. Most standard thick film resistors do not handle large pulses of current very well and will eventually degrade and even fail. Therefore, other technologies should be considered for high pulse current applications like gate resistors. In terms of gate resistor options, here are a few from Vishay that would be worth considering. Although there are many high pulse handling resistors in the market, the Vishay CRCW-HP offers superior performance due to its double-sided resistive element, thereby offering more power in the same package size, resulting in space savings on the PCB. For example, the 0805 package size can handle up to 1/2 watt and replace a standard 1210 package size. In addition, the CRCW-HP can be used to handle high pulses, transients, ESD, or other surge conditions, either in gate resistor or snubber applications. Another great fit for high pulse applications are MELF resistors. MELFs are one of the most robust, stable, and reliable resistor technologies available, combining the most important technical features in a single component. The best pulse capability for a surface mount resistor, with the largest effective resistive area and mass due to the cylindrical design, sulfur resistance, and full RoHS compliance without exemption. They are available in 3 case sizes and can handle up to a 10 kV 1.2/50 microsecond waveform with the CMB0207 series. In order to provide continuous current monitoring for both control purposes and overload protection in either operating mode, 2 Vishay WSLP 3921 current shunt resistors are utilized in each phase, labeled R1 and R2 in the schematic. A 2 milliohm resistor was used on the 48 volt side, and a 0.5 milliohm resistor was used on the 12 volt side. A differential voltage measurement is taken across each current shunt and then fed into a current sense amplifier, which I'll describe in more detail in a few minutes. One quick comment on an overload condition. During the short amount of time it takes for the overload current to be recognized and the microprocessor to respond and turn off all the switches, the MOSFETs can handle a considerable amount of overload current due to the high pulse drain current capability of a bond wireless MOSFET, which I discussed a few minutes ago. Taking a look at the layout again, you can see the two current shunts and how they're situated in relation to the power MOSFETs that are being switched based on the current measurements. I wanted to take a few minutes to explain why a current shunt technology was selected for this design. In most high current applications, like this one or maybe a motor drive, their current needs to be monitored for control purposes or overload protection. There are two methods that are commonly used for this purpose: a resistive current shunt and a Hall effect sensor. A Hall effect sensor is relatively simple to implement as a turnkey solution compared to a current shunt, which requires some additional feedback circuitry, but it can suffer from the following disadvantages: low linearity over a wide current range, offset error due to wide variations in the temperature. There can also be excessive measurement latency and bandwidth limitations depending on the switching frequencies being used. And a Hall effect sensor will also saturate when its current range is exceeded and will be unable to provide an accurate measurement. In addition, a Hall effect sensor requires a separate power supply for operation. And finally, the overall system cost tends to be somewhat higher with all things considered. One more point: customization of a Hall effect sensor is usually not cost-effective or even possible, whereas a Vishay current shunt can be configured to meet the mechanical constraints of the system, either in one of the many standard packages from 0603 to 5931, or a customized version of the larger 8518 shunt. As mentioned before, the WSLP 3921 was selected in this design. The Vishay power metal strip design features an all-metal welded construction, so in addition to the benefits described in the previous slide, it can also handle very high pulse currents that can occur during overcurrent or short circuit conditions. The WSLP 3921 offers the lowest possible resistance values of the surface mount power metal strip series, down to 100 microohms, and it also offers the highest power rating of up to 9 watts in this package size. The WSLP 5931 can also be used if even higher power ratings are required, up to 15 watts. In addition, the raised element package, as you can see highlighted in the red box, keeps the resulting hotspot away from the printed circuit board, which may not be able to handle the same operating temperature. If needed, the WSLT 3921 series extends the temperature range up to 275 degrees C for high ambient temperature conditions, such as underhood applications, or for added headroom with the necessary derating curve. I also wanted to mention a very useful design tool when using current shunts in pulse applications. Vishay's online pulse calculator allows designers to select the product series, enter the desired resistance value, and modify the ambient temperature conditions. The resulting pulse capability curve is specific to that particular part and value, and there's also an option to change the curve between energy and power capability. The chart consists of 3 zones that display the capability curve over time. The first zone is defined as a pulse, which is generally less than 20 milliseconds. This is a short transient that it causes a temperature rise in the resistive element. The transient is too fast to dissipate to the surroundings, so the energy is limited to the mass and thermal limit of the resistance element. As the pulse duration extends into the surge region of time, the energy can transfer to the terminals. This increases the mass available for dissipation, and so the energy capacity increases over this period. The last zone is the region of short time overload rating. It defines the maximum energy capacity of the part, including the circuit board. Here's a detailed view of the current sense amplifier that was used to take that very small voltage in millivolts that's measured across the shunt and amplify it to a voltage level that can be used for control and protection by the microprocessor. The primary storage inductor, labeled L2 in the schematic, in each phase needs to support both the DC output current along with the ripple current. The ripple current amplitude is determined by the switching frequency and inductance value. Increasing the switching frequency or the inductance value will reduce the ripple current, but there are trade-offs in size and performance that must be taken into consideration. In addition, the designer must ensure that the inductor is rated for the desired output current for both self-heating and saturation. Taking all of these factors into consideration, a Vishay IHDM inductor was selected for this design. Taking a look at the layout, you can see the centrally located phase inductor in relationship to the switching MOSFETs and the current shunts. The Vishay IHDM inductors are a great choice for this application since they have a good combination of low DC losses, low core losses, that is AC losses, and the best saturation performance of any of the inductor material choices. They feature a powdered iron construction, similar to our standard IHLP automotive inductors, which will be covered later, that provides a soft saturation performance, as shown by the blue curve on the graph, in comparison to a ferrite, which exhibits hard saturation, as shown by the red curve. In addition, the IHDM series cover a wide range of inductance values, from 0.1 microhenry to 200 microhenries, with current handling capability from just a few amps to several hundred amps. These inductors are also available in several materials that allow efficient operation at frequencies from 100 kHz up to 5 MHz and operation up to 180C. They are also easily customizable in terms of the inductance value, voltage rating, terminations, and mounting orientation to meet the requirements of many 48-volt and high-voltage automotive applications. In order to suppress the ripple current that is generated by the high-frequency switching of the power MOSFETs, an LC filter is required for both the 48-volt and 12-volt bus connections. The combination of L1 and C1 is shown in the schematic on the 48-volt side, and L3 and C6 on the 12-volt side make up the input-output filters that reduce the ripple current imposed on the battery voltages. For the filter capacitors, a 47 microfarad 80-volt part was used on the 48-volt side, and a 330 microfarad 25-volt part was used on the 12-volt side. Either a high-temperature standard aluminum electrolytic with an appropriate ripple current rating or a hybrid conductive polymer aluminum technology would be a good choice for this application. For the filter inductors, a 3.3 microhenry Vishay IHLP 4040 was used on the 48-volt side, and a 0.33 microhenry IHLP 5050 was used on the 12-volt side. In this case, the Vishay IHLP series was used for the filter inductors, for the same reasons outlined previously for the main storage inductor. I'll discuss the IHLP technology in more detail later in the presentation. Taking a look at the layout again, you can see the two sets of LC filters located in close proximity to their respective 48-volt and 12-volt bus connections. Just a quick comment on voltage sensing, since it's required on both the 48-volt and 12-volt buses. In order to make sure the voltage dividers used to make these measurements don't drift over temperature and time in the field, a precision pair of resistors should be used for any critical voltage measurements that are used for control or protection. Therefore, a precision thin film technology as opposed to a standard thick film technology, should be selected for this type of application. To meet the performance requirements of this design, the Vishay ACAS precision array was selected in a 2x configuration. The Vishay ACAS array is available in either a 2x or 4x configuration, and resistances of any value can be freely selected for each of the resistors, up to a 1 to 100 ratio. Due to the thin film technology and the fact that the individual resistance elements are manufactured on a common substrate, you can get very impressive individual tolerances down to 0.1% and matching tolerances down to 0.05%. In terms of the relative temperature coefficient, you can get down to 5 ppm tracking between the resistors. All of this results in uniform thermal stability and equivalent aging drift over time for individual resistors on a common substrate. This series also offers a broad resistance range from 47 ohms to 221K, operating temperature up to 155 C, and working voltages up to 100 volts. Another possible solution for a precision voltage divider would be discrete thin film resistors. The Vishay TNPW series is the best-in-class thin film resistor series offered by Vishay for long-term stability with less than 0.05% drift after a 1,000-hour life test. This series is available in sizes from 1210 down to 0201, resistance values from 1 ohm to 3 meg, and tolerance TCR down to 0.1% 10 ppm. The TNPW offers superior 85/85 biased humidity performance and is also sulfur resistant. The power rating upgrade is highlighted in yellow in the table. For example, up to 0.1 watt for an 0402 package size compared to 0.063 watts as the industry standard for this size. If even tighter tolerance and TCR are needed, the TNPU Ultra Precision is available with tolerance and TCR down to 0.02% and 2 ppm. In order to provide power for all of the control circuitry in each of the 6 phases, an 11 volt and a 5 volt regulated power supply were required. To minimize the space required, an integrated synchronous buck converter was used for each of the supplies, which I'll describe in more detail on the next couple of slides. The 2 power supplies were very similar in design, so I'll just be focusing on the 5 volt version. Looking at the layout, you can see that only a very small section of the control PCB for one of the phases was required for the complete power supply. The 5 volt supply is shown here on one of the 6 phases, and the 11 volt supply was located on another one of the phases. Here's some more details on the synchronous DC to DC converter, which is a Vishay Microbuck series product. The actual part used in this design is from a commercial family, but we are in the process of releasing an automotive grade version as shown here. It's an integrated multi-chip design that incorporates the control IC and both of the power MOSFETs in a 5x5mm package. The only other components required are the storage inductor, an output capacitor, and some small resistors and capacitors to set some of the control parameters. It has a very wide input range from 4.5 volts to 65 volts, so it can be used in just about any automotive application, either on the 12 volt bus or on the 48 volt bus. The output voltage is adjustable to any value down to 0.8 volts, and there will be 2 output current options, 6 amps and 10 amps. It's also a highly configurable system, with the switching frequency being adjustable anywhere from 100 kHz to 2 MHz, and the soft start and current limit functions are adjustable as well. Samples of these new automotive grade products are planned for Q4 this year. I also wanted to spend a few minutes on the details of the storage inductor that was used for the power supply. In this case, a Vishay IHLP 2525 22 microhenry inductor was selected based on the selection criteria described in the microbuck datasheet. Looking at the layout, you can see that the storage inductor is located in very tight proximity to the microbuck converter chip. The Vishay IHLP family of inductors come in a wide range of sizes, from the IHLP 1212, which is 3 mm by 3 mm, up to the IHLP 8787, which is 22 mm by 22 mm, and are available in various heights. They feature a powdered iron construction, which provides a soft saturation, which I'll talk about in more detail in a few minutes. The low-profile package and wide terminations provide excellent mechanical shock and vibration performance, especially in engine-mounted applications. The IHLP inductors also exhibit very impressive current ratings. For example, a 1 microhenry IHLP 8787 is rated for continuous operation at 69 amps, which is defined as the DC current that will cause an approximate increase in temperature of 40 degrees C. These inductors can also be operated up to 180 degrees C, which I'll also talk more about in a few minutes. The IHLP technology was originally created and patented by Vishay and features a very unique construction. The high-temperature copper magnet wire is wound first and then ultrasonically welded to a copper lead frame that is plated with nickel and tin. Then a proprietary blend of low-loss iron powder is pressed around the winding and lead frame at a very high pressure, and the resulting assembly is cured at a specific temperature, which results in a very compact inductor. There is no wasted space since an air gap or bobbin is not required, as you might find in the construction of a typical inductor. The copper wire and lead frame carry current, and the powdered iron carries flux, which results in the most efficient inductor possible in terms of volumetric density. In addition, since the winding is completely contained within the magnetic material, you effectively get a magnetically shielded inductor without having to add a separate shield as you might find in other products. Also, due to this composite construction, these inductors exhibit ultra-low buzz noise. In terms of the saturation characteristics of the IHLP compared to a standard ferrite inductor, there's a drastic difference in performance. The red curve illustrates a typical ferrite inductor as the current is increased for a given inductance value. The curve is very flat up to a certain current level, known as the saturation point, at which there is a significant drop in the inductance. As the current continues to increase, the inductance continues to drop until the inductor behaves more like a resistor, which is obviously not the desired result in most power supply or filter designs. In contrast, the blue curve illustrates the typical performance of an IHLP inductor. As the current is increased for a given value, the inductance decreases very slowly at a nearly linear rate, but never reaches a hard saturation point like the ferrite. This is a significant advantage in performance, knowing that your inductor will continue to behave like an inductor over the entire range of current. It also allows the power supply or filter to handle high transient current spikes without saturation, which improves the ruggedness and reliability of the system. It should also be noted that even though the powdered iron IHLPs do not hard saturate, we still define a saturation current on all of our data sheets. Since the inductance does decrease to some extent as the current increases, we define saturation as the DC current that will cause the inductance to drop to approximately 20% of its initial value. We also provide the inductance versus current graphs for each value on all of our data sheets. Furthermore, a ferrite inductor is very sensitive to the temperature. As the operating temperature is increased, that same red curve will shift to the left and continue to do so as long as the temperature keeps increasing. The result is an even lower current saturation point, which typically results in using a larger, more expensive inductor to prevent saturation at the worst case conditions. The IHLP inductors, on the other hand, do not exhibit any temperature influence whatsoever with regard to saturation. That same blue curve for a given inductance value will look the same whether the inductor is being operated at minus 40 C, room temperature, or at the maximum operating temperature. Again, a huge advantage when designing a power supply or filter. One more benefit of the IHLP family of inductors is the material options that are available. When this technology was first created and released for production, there were only two material choices available, both topping out at 125 C with regard to the maximum continuous operating temperature. The -A1 material was optimized for very high frequency operation, up to at least 5 MHz, so it exhibits the best saturation performance and lowest AC core losses possible. The -1A material, on the other hand, was optimized for the lowest possible DC resistance. It still has good frequency characteristics, up to at least 2 MHz, and the AC core losses and saturation performance are still reasonable. In the years since the inception of the IHLP, there has been continuous improvement in the iron powder technology in terms of temperature and frequency response. There are now two more options with regard to the maximum continuous operating temperature. The -5A material can be used up to 155 C, and the -8A material can be used up to 180 C. Both of these materials have been optimized in terms of the core losses and DC resistance, so the resulting frequency response and DC losses are a good compromise between the -A1 and the -1A materials. There is another relatively new product that is worth mentioning as it is becoming quickly adopted by many of our key automotive customers. The Vishay IHLE is our standard IHLP with the 155 C material that's been outfitted with a shield to contain the electric field emissions. If you remember back to the construction of the IHLP, the winding is completely contained within the magnetic material, so you effectively get a magnetic shield for free. However, the construction does not contain the electric field, nor does any other type of inductor for that matter, since that's the function of a capacitor. Therefore, during radiated emissions testing for EMC compliance, the inductor tends to be the chief offender in many cases when the test limits are exceeded. There are several potential remedies, which include an external shield over the inductor or the entire power supply, using an appropriate enclosure as a shield, or trying a new printed circuit board layout. All of these methods can add a significant cost, complexity, and time depending on the severity of the problem. In contrast, using an IHLE from the beginning of the design, or swapping out an IHLP if the printed circuit board has already been laid out with the additional two terminals for the shield, can be a quick and very cost-effective solution. The results will vary from one design to another, but reductions up to 20 dB in the electric field, when measured at a distance of 1 centimeter above the center of the device, have been achieved. The IHLE is currently released in the 25-25, 32-32, 40-40, and 50-50 sizes, with the smaller 20-20 size coming later this year. Since this DC to DC converter is a reference design and will need to be modified for a specific set of customer requirements for production, there was no transient voltage protection included in this initial design. Typically, some type of transient voltage suppressors will be required in order to protect all of the downstream components from high voltage or high energy transients that can be induced on either the 48 volt or 12 volt bus. This type of device will absorb the energy contained within the unwanted transient pulse and clamp the resulting waveform to a level which is no longer harmful to the remainder of the components in the module. An excellent choice for this type of application would be the Vishay XMC7K24CA Transient Voltage Suppressor, which features a new X-clamp or snapback technology with an extremely low clamping voltage ratio for suppressing transients to lower clamping voltages than conventional TVS devices. It features a 24-volt working voltage in a bidirectional arrangement and has a very high pulse load capability, up to 7,000 watts for a standard 10/1000 microsecond pulse, all in an SMC package. It can also be paired with other TVS devices to achieve other working voltage levels. As you can see from the current versus voltage graphs on this slide, the X-clamp suppressor has a much steeper slope compared to a conventional device, which results in a much lower clamping voltage for the same level of peak current. In order to obtain other working voltages for a specific application, this part can be connected in series with another transient voltage suppressor, for example the Vishay 5K-AS MC family. In this design, for example, on the 48-volt side, the XMC 7K24CA could be paired with a 5K-ASMC30A to provide a 54-volt working voltage with a very low clamping voltage capability. I'd like to cover one more topic before wrapping up this presentation. Although the phase switching MOSFETs are sized to handle the maximum load current, it's still a good idea to monitor their operating temperature in case of unforeseen circumstances such as excessive ambient temperature or maybe an overload on either the 48-volt or 12-volt bus that could cause excessive heating in the MOSFETs. Therefore, a Vishay surface mount NTC thermistor, labeled NTC1 in the schematic, was selected to monitor the temperature. As you can see on the layout, the thermistor is placed as close as possible to the group of phase switching MOSFETs. Therefore, the heat generated by the MOSFETs will make its way through the printed circuit board and result in a corresponding temperature rise in the nearby thermistor. The feedback circuitry required for the thermistor is shown on this schematic. A voltage divider is set up with the thermistor from a precision voltage reference. The resulting voltage is then fed into the microprocessor for monitoring. The Vishay thermistor selected for this design is from the NTCS family. They can operate up to temperatures of 150 C and are glass coated and protected. They also have a flexible polymer termination to resist board flex and solder cracking due to thermal cycling. In this design, an 0805 size was selected, but they are also available in an 0402 and 0603 size. Available 25C resistance values range from 2K to 680K, and the B value ranges from 3420 to 4125 Kelvin, with tolerances down to plus or minus 1%. In summary, a new 3 kilowatt, 48 volt to 12 volt bidirectional DC to DC converter has been presented that can be used in any dual board net system. This design also featured a 6-phase topology that can disable phases as necessary to maximize the overall converter efficiency, in this case up to approximately 97%. Okay, this concludes the presentation. Thank you for your time today. I hope it was informative and relative to your applications. And please keep Vishay in mind for any discrete component solutions in your new designs.